Hey guys, today we're doing Chapter 3, Section 4 for Math 1. We are going to look at some rotations again and reflections, and we're just going to verify some of the properties that each of these have. And probably the important thing here is just to see how to verify the different properties, I guess, and to know what the properties are. So here we go. The first thing we're starting with is the properties of a rotation. And you can see there's three of them listed here. A rotation around a fixed point. Most of the time we rotate around the origin, but as you'll see, we can also rotate around any point really. It preserves the distance between all points and the point of rotation. So here's what that means. It means all angle measures in a figure are preserved. Preserved is just a fancy word, means they stay the same. All segment lengths are preserved. And the angle formed by an original point and its image, both connected to the center of rotation, will be equal to the angle of rotation. That's a little weird. I will show you what that means. Okay, these first two that say all of the measurements are the same, this is what makes this a rigid motion. A rigid motion is just a transformation that keeps everything the same, or it keeps all the measurements the same. That's what it means to be rigid. All right, so we are going to start out by performing a rotation. I have this empty graph here, and I'm going to have you draw a mini X and Y axis. You'll want to draw that in the middle of the graph. So it might look something like, you know, how about this and this. So there's kind of my X and Y axis that I'm going to work off of. And I am going to graph the points. I really wish I had done this ahead of time. I'm going to graph the point 4, 1, and 2, 5. 1, 2, 3, 4, 1. So here's point A. And point B is at 2, 5. 1, 2, 1, 2, 3, 4, 5. Here's point B. Maybe I connect them with a segment, maybe not. But now comes the drawback to not doing this ahead of time. I'm going to rotate this thing 90 degrees counterclockwise. Well, fortunately, we already looked at how to do this, so I don't feel too badly. But to rotate this thing 90 degrees counterclockwise, right, that would be in, so that would be in this direction. And I want to rotate 90 degrees. So I grab my paper and I rotate it 90 degrees this way, which is 1/4 of a turn. And that would take me to about right there. Now, unfortunately, because I did not do this ahead of time, my red segment did not rotate with me. So that is unfortunate, but I can fix that real quickly here. So that would have ended up, let's see, that is where A ended up and B was here. And that is where your segment should have ended up when you rotated 90 degrees counterclockwise. All right, the CCW, counterclockwise. So, of course, after we rotate it, we want to note where the image of A and B end up. A ends up at -1, 1, 2, 3, 4. So A prime is at -1, 4. That is where A ended up after the rotation. And B prime, after it was rotated, 1, 2, 3, 4, 5, -5, 2. That is where they ended up. So now I can go ahead and rotate my paper back to its original position. Bam. And I can redraw it And look at that, it's already drawn for me. This is now A prime and B prime, whereas the original A was here, and the original B was here. And you can see that segment has rotated around the origin 90 degrees counterclockwise. All right, so that is a review of how to do a rotation. And we want to verify a couple things here. We want to verify that angle AOA prime equals the angle of rotation. So let's look at how to do that. Angle AOA prime. So right here is point O, the origin. So when it says angle AOA prime, it means start at A, go to O, and then go to O prime. And we are looking at this angle right here. And we want to verify that that angle equals the angle of rotation. So the angle of rotation was 90 degrees. Can we verify that that angle is 90 degrees? Well, sure we can. We need to verify that that is a right angle. And the way to verify that that is a right angle is to check the slope of both lines. So I'm going to check the slope of the segment A prime O. That's this big segment, right? The slope of that would be 1, 2, 3, 4, 1. It would be negative. The rise is -4. The run is 1. So I would say, let me fix this a little bit. I would say the slope A prime O equals -4 over 1. And, oops, then I'm going to check the slope of the other side of the angle, which is AO. The slope of AO is, let's see, it's 4 and 1. It's positive 1 over 4, the rise and the run, right? The slope of AO is positive 1/4. And because these are opposite reciprocals, we know that it is perpendicular, right? So therefore, they must be a 90-degree angle. And we have verified that that angle, this angle right here, must be 90 degrees because those lines are perpendicular to each other, because their slopes were opposite reciprocals. Okay, so what's the other thing we want to verify? Verify that these segment lengths are preserved. Okay, I'm going to go through this once here. How do we verify that the segment lengths are the same? So what we're looking at is, we are looking at this segment length versus the original segment length, right? Well, here's how you're going to do that. You are going to find that segment length. And one way to find it is to make it a triangle, like a slope triangle, like this. So now I have like a triangle here. And I'll do the same thing over here. And I have a triangle here. And not only is this a triangle, it's a right triangle. And the bottom side has a length of 4, and the right side has a length of 2. Oops, I can count. So I can now use the Pythagorean theorem, which hopefully you remember, but I'm going to go over it. And I can find the length of B prime A prime. And it would look something like this. 4 squared plus 2 squared equals B prime A prime squared. the length of B prime, not B prime A prime. Yeah, B prime A prime, that's right. So we go back. So one side of the right triangle squared plus the other side of the right triangle squared equals the hypotenuse of the right triangle squared. All right, that is the Pythagorean theorem. And as I solve that, I would get 16 plus 4 equals this B prime A prime squared. That would be 20 equals B prime A prime squared. And to solve that, I would take the square root of both sides, and I would get B prime A prime equals the square root of 20. That is the length of that side of the triangle. So let's look at the other one. Now I'm looking over here. Is segment BA the same length? And I think it's obvious that it is, but look, we have the same triangle. This side of the triangle is 4, and this side of the triangle is 2. And then I have side BA. So when I set up the Pythagorean theorem, it would be, again, 4 squared plus 2 squared equals, this time it's BA squared. I guess that should be in parentheses technically. And that's still going to give me 20 equals BA squared, which is going to give me that BA equals the square root of 20. So we can see here that when I rotated the segment, the length of it was preserved. So what I have done is I have verified this, that the angle measures, well, I didn't actually verify that one. I verified this one, that the segment length is preserved. And I verified this one, that the angle formed by an original point and its image, both connected to the center, will equal the angle of rotation. All right. So this brings me, I want to get something. This brings me to, this is what I want. We're going to practice doing a couple rotations around a random point. So when you're going around a random point that is not the origin, what I do is I make it the origin. Even if it's not the origin, I would draw a X and Y axis there, and I would pretend it's the origin. And so to rotate this 270 degrees clockwise, I could go 270 degrees that way, or that would be equal to going 90 degrees that way. Both of those would end up in the same spot. So that is what I'm going to do. I'm going to take this figure and I'm going to rotate it 270 degrees. That's 90, 180, 270. Or as you can see, I could have just gone 90 degrees the other way. And we are going to look and see where this thing ended up. So let me record a few things. So this point ended up at negative 3, 1, right? And this point is at 0, negative 1. And this point is at 1, 2, 3, negative 1, negative 3, negative 1. And finally, this corner is at 1, 2, negative 4, 0. So I have recorded where my shape ended up after the rotation. Now, of course, I can go ahead and put it back to the original place. And look at that. That is beautiful for me. I've already graphed them. So I now take these points. Oops. I now take these points and I regraph them. Here they are. They're already on here for me. That's a good way to do it. And I reconnect them. And I have rotated that diamond 270 degrees clockwise, right? Okay, so the other one is 180 degrees. And I wanted to show you a different way to do this one maybe. You know, I could do it the same way. I could just take my paper and I could rotate it 90, 180, and that's where my shape ends up. And probably that's the best way, safest way to do it. So let's go ahead and do that. Let's mark all those points. This is where they end up. I could record those points, right? I could record those points by making this a little X and Y axis and saying, you know, I have a point like right here at 0, 1, and I could record all those points and then rotate my paper back and put them on the paper. But I actually don't need to do that because I think they will stay right where they are. And hopefully this will still work. Oh, this one's not as symmetrical for me. How sad for me is that? So I guess I'm going to have to go ahead and record them. A little disappointing for me. So I'm at 0, 1. I'm at negative 1, 1. I'm at negative 1, 3. I'm at 1, 2, 3, negative 3, 0. And negative 3, 3. And negative 4, 1. And I'm at 0, 0. Okay. Now, I think I can go ahead and do this and rotate it back. Boom. And let me graph those points again. So 0, 1, negative 1, 1, negative 1, 3. I'm just pretending that this point right here in the middle is the origin. Negative 3, 0. Negative 3, 3. Negative 4, 1. And 0, 0. Did I do it right? I hope so. So there is my shape, rotated 180 degrees clockwise or counterclockwise because it would be the same thing. All right, so last up here I got these properties of a reflection. And we are going to verify these as well. Let's see, we start with all lines connecting a point to its image will be parallel. I'll tell you what, I will verify them and then I will come back and read these as we have done. So we're looking at this diagram, and the first thing it wants me to do, okay, so it's a reflection, right? I've got a line of reflection, and you can see triangle QPR and triangle Q prime, P prime, R prime, which is its image. And it wants me to connect P and P prime. So that would be those. And Q and Q prime. That would be those. And R and R prime. That would be those. And it wants me to make an observation. And the observation I'm going to make is I think those lines look parallel to each other. But I'm going to check. And I can check to see if they're parallel by checking their slope. Now, this is not my favorite graph. Let's see. So I'm doing the slope. So I'm going to start with PP prime. It's not my favorite graph because some of the points are at halves, but I will deal with it. So the slope of PP prime would be this right here, right? So that is down 1 and over 2. It is negative 1/2. The slope of Q prime, that would be down 2 and over 4, which is also reduces to negative 1/2. And the slope of R prime, that would also be down 2 and over 4, which also reduces to negative 1/2. And so because the slopes are equal, I know that means the lines are parallel. And what I have done there is I have verified that all lines connecting a point to its image will be parallel. Check. All right. Next up, we want to look at R prime and the line of reflection. So let's do this one in red maybe. So here's R prime, and here's the line of reflection. Let's see, that's a good point, good point. And we want to make an observation here. And I think the observation we want to make here is that those lines are perpendicular to each other. And how can I check and see if they're perpendicular? By checking the slope, right? So again, I'm going to be doing the slope of R prime. I see I shouldn't have had a prime on that. And that, we already know that's -1/2. We just did it in the last problem. How about the slope of line L? So line L has a point here and a point here, and it looks like I am up 2 over 1. And you can see, obviously, these are opposite reciprocals. And because they're opposite reciprocals, we know that the lines are perpendicular to each other. So it looks like I have verified that the line connecting a point to its image will be perpendicular to the line of reflection. Check, I have verified that. And last up, I'm supposed to look at, on the segment R prime, where it intersects line L, we're going to call that point N. So it's asking me to call this point right here N. That is where the R prime intersects the line of reflection. And I want to make observations about Rn and R prime N. I'm not really going to do this, but I want to show you. They want me to prove that this length is equal to this length. And so to do that, I would do the same thing I did in the first problem we did. I would set up the Pythagorean theorem and prove that those two lengths, based on the Pythagorean theorem, have to be the same. And I don't think I need to do that. I think we're okay. I do want to point out one thing, and we'll be done. And it's this. Rn, you can come in, Rn. These are 4 different ways to write Rn, and I just want to make sure you know what they mean. So this means a segment, which means it has 2 endpoints. And this means a ray, which means it starts at R and goes all the way through N, has 1 endpoint. This is a line. It goes forever in both directions. But this one, when there's nothing above the R and the N, actually means the distance from R to N. That is what it means when these 2 letters are next to each other and have nothing over top of them. All right, that's it. You're ready for the homework. See ya.